Good morning, Algebra 1 superstars, and welcome back to your Topic 1 lessons on solving equations and inequalities. The lesson we're about to do today is Lesson 1.5, Literal Equations. This is a really nice lesson to somewhat end our short section on solving equations, and it's actually an easier lesson than anything we've done so far, at least in terms of you won't have to add and subtract numbers together, nor will you have to multiply and divide too many. There'll be a couple examples. So let's go ahead and jump into this, and I think you're going to find a lot of success today. Because it's really just applying what we've already learned, but in a slightly different way, and again, with a little less work. So, your opener for today is to try two sets of problems. You're going to try 1a, solving for x, and then 1b. Then you'll try 2a and 2b. After you try each of them, make sure that you pause the video first, try them, and then unpause. I'll discuss the similarities and differences and how solving 1a will help you with 1b, and so on and so forth. Ready, set, go. Okay, so hopefully you've unpaused at this point, and maybe you didn't have too much trouble with this one. If you did, I'll just remind you, we're just following SADMAP. We always want to undo addition and subtraction first. There are two numbers on the same side as x. 2 is multiplying, 3 is adding. So let's undo that adding 3 by subtracting it from each side. That leaves us with 2x equals 10. And then there's only one step left. The 2 is multiplying, so we need to divide that 2 from each side. Anything divided by itself is 1, and that gives us 5. Only 2 steps to solve. It's a 2-step equation. We did this in lesson 1.1. So let's go ahead and compare that to 1b. Well, 1b actually looks exactly the same as 1a, except instead of 3, they have another letter in the equation. Now, you can call this letter a variable, or you can call it a constant. I think most people would probably think of this as a constant because it can be a single number, but you could consider it a variable too. You can pick anything you'd like for it. The nice part is, though, whether there's one letter or two, or numbers or variables, they all behave the exact same way. So if I was able to subtract 3 from both sides here, then if I'm trying to solve for x, I should be able to subtract b from both sides as well. So let's take a look at this. Right? So we have this 2x plus b equals 13. I'll keep my same colors. I'm going to subtract b from each side. When I subtract b from each side, positive b minus b cancels out. But then the question becomes on this right side, what do we do? Well, we have a 13 and a b. Does this become, and you might not want to write this because I'm going to change things up, does this become 13b? Negative b times 13? 13 minus b? Well, the answer is none of those are really correct. I see a lot of students first put 13b, and I shouldn't even put that. They do this because they think there's a 13 and a b and they need to be next to each other. But don't forget that whenever you write two, we'll call them terms, right next to each other, that always means that they're attached by multiplication. But we're not doing multiplication up here, we're doing subtraction. And because we can only add or subtract like terms, and 13 and b are not like terms, then we write this as 13 minus b. And that's it. So there's actually a little less math that we had to do here. Because on this side we had to do 13 minus 3, and then we actually had to do 13 minus 3 to get an answer of 10. You're like, well, I can do 13 minus 3. Well, that's true, but what if it was 974 minus 12.715? Then the math gets a little obnoxious. But on this right side, we didn't have to do any, we would probably call this arithmetic, addition, subtraction, multiplication, and division. We didn't have to do any of that. We just got to write them directly next to each other. Okay, let's finish this off. 2 was multiplying times x, and over here we went through and divided by 2, so I'll do the same. Now, when you divide by 2, it's usually a good idea, whenever you multiply or divide a side, to group that in parentheses, and we've seen this before. So I'm going to group that whole side in parentheses, and then do divided by 2. These 2's, of course, cancel each other out, and we are set. 13 minus b over 2. And it is optional. You don't have to put the parentheses like I did. I think it's a good idea so that you remember 2 is dividing to everything in there. But if you'd like to leave them off, that is okay as well. And this is our answer. Notice that we didn't actually get a value like we did on part 1a. We just essentially moved everything that was attached to the x over to the right side. Now, we might want to do that because if we found a value for b, like we said, oh, b is 10, what is x? Well, if b is 10 and we wanted to know what x is, then you would have to solve this equation and figure out x. But if I know b is 10 and we already have this form of the equation, then we can just replace b with 10. We do 13 minus 10 divided by 2, and we're done. So isolating a variable when there are multiple different letters or variables or constants in an equation is useful if you know you're going to be trying different values for that variable. And we'll see some examples of this near the end of today. All right, let's move a little bit quicker. So 2a, we had to isolate x. Unfortunately, there are 4 possible starting steps here, and I am going to at least put the 1 in front of the x. Remember, your 4 steps, we are down to, there's no distributive property, we can't combine like terms, we're down to the addition and subtraction step. Everything here is positive, so we have to subtract something from both sides. Your 4 options are subtracting 5x from each side, subtracting 4, subtracting 1x from each side, or subtracting 20 from each side. And all of them are acceptable steps. They will all get you the right answer. My personal preference, as I mentioned last time, is I always like to subtract the x's first, and in particular, I like to subtract the x that keeps all my x's positive. So I think subtracting 1x from each side will keep all of my x's positive. So that gives us 4x plus 4 equals 20. Once we're here, now this left side has all the x's, and now it's just a 2-step equation. There are 2 numbers attached to x. 4 is multiplying, and this 4 is adding. We know we're still in that SA part of SADMEP, so we need to undo adding 4 from each side. This gives us 4x equals 16. And then we can finish this off, because since 4 is still adding or multiplying by x, we want to divide by 4. I've mostly run out of room here, but I think we can do the math. This just gives us x equal to 4. All right, let's follow those same steps, but now instead of 4, we've replaced that with the variable d. Same steps to start, though. Let's go ahead and subtract 1x. Those are like terms. 4x plus d equals 20. Then what did I do next? I think next I subtracted 4, but I don't have 4 anymore. I have d, so I'm going to go ahead and subtract d. This leaves me with 4x equals 20 minus d. Again, less math here. We don't have to actually divide this off. I've run out of room, so I'm going to go ahead and rewrite this up above. And I think we can probably remember our last step, which is almost certainly dividing both sides and grouping by 4. And we get to finish with x equals 20 minus d divided by 4. That is really as difficult as today gets. So we're going to be solving the same types of equations that we did last class, but instead of having all x's or numbers, we might introduce another variable or another letter or even more than just one. And we have to use our same steps, adding, subtracting, multiplying, dividing, to pull everything to one side so that we isolate the asked for variable. So, in conclusion, why do I think the B problems are easier than the A problems? I think the B problems are easier than the A because you actually have to do a little less math, or in particular, we'd probably say less arithmetic. I may have spelled that wrong. That's probably an E. There we go. And that's because we don't have as many like terms, right? 20 minus 4, that's a nice little like term here we had to combine, but 20 minus D, we didn't have to do anything. And so there's actually less of a chance of you making a mistake because you won't be making mistakes with negatives or division or anything like that. Now, another step. The B problems in the right-hand column, these guys over here, are generally known as literal equations. Any idea why? Well, literal actually comes from, the stem of literal comes from the same stem as the word letter. And so literal equations are essentially just equations with letters. Or in particular, you're like, but all of our equations have had letters. They've had the letter x. More letters than just x, right? It's very common if you sneak a peek down at 1b to have just letters or constants or variables instead of any numbers at all. So literal equations are really just equations with, and I'll put this in parentheses, more letters. Okay, so before you guys get some practice in, I have one more problem that I'd like you to look at. And I say one more because you'll notice that 1a and 2a are the exact same problem. I bet you guys will be able to figure out 1a and 1b on your own, but I wanted to show you an alternate way to solve this problem that sometimes comes up, and then we can have a good discussion about their answers too. So go ahead and pause me, make sure you can solve 1a, and by the way, you'll do it right if you get an answer of -6. Work 1a until you get -6. Try 1b the same way you did 1a, and then we will come back and go over the rest. Ready, set, go. Okay, you're back. So let's go ahead and solve this. I imagine most of you probably did the same first step, where you distributed your -3. Remember, we're distributing multiplication here because 3 is attached by multiplication. -3 times x is -3x. -3 times 4 is -12. And the other side has not changed. Now we just have two numbers that are attached to x. 12 is subtracting. -3 is multiplying. So let's undo the subtraction first. We add 12 to each side. 12 and 6 are like terms, which means we have to do a little bit of math here. 6 and 12 gives us 18. Last but not least, -3 is multiplying times x, so we need to divide off everything that's multiplying, including the negative. Those make a 1, and we end up with x equals -6. So really 3 steps: distribute, add, divide. Let's see if we get the same thing over on the right. Well, we're going to distribute. Now when we distribute this, we're like, wait, how do we do a times x? Well, because they're not like terms, again, we get to do less math. We just show that we're doing a times x. And then same thing, how do we do a times b? Well, we do a times b. And I left off the dot on this one. I could have left off the dot over here too, because we know if you have two variables right next to each other, it's always assumed that they're multiplying. If it makes you happy, you can put the dot, but again, you don't have to. And then the right side still says equals c. What's next? Well, next we had to undo everything that was attached to x. And I see two numbers, and it's kind of hard to see this, attached to x. A is attached by multiplication, and AB is attached by addition. This is all one number. If you think about that dot connecting them, I like to think of that dot as like glue. So A and B are stuck together, and we treat them as a single term. So I want to isolate x following SADMAP. Our first step is to subtract that AB from both sides. I'm going to subtract this over here. You might notice that I didn't line up the AB with C, and that's because they are not like terms. When I do the subtraction, it's even easier than 6 plus 12. You just write them next to each other. Last but not least, we need to go through and remove the a that's multiplying by x by dividing both sides by a. And that leaves us with x equals c minus a times b, all divided by a. And that's it. Now, I did promise you a second way to solve this equation, right? And our second way to solve has to do with the fact that looking at the parentheses, there's just a -3 that's multiplying. That's it. And so what we're actually able to do in this case is we're actually able to divide all of this by -3. Now, this is, again, a trick that doesn't work all the time. It only works in a situation like this, where the -3 is on the outside. It's not doing anything to the x plus 4 yet, so we're actually going to cancel out the -3 before distributing, going a little bit out of order. But I think you'll actually find here that when we divide, don't forget, both sides by -3, this will actually be a bit of a faster process than before. 6 divided by -3 is -2. And then actually noticing we took away the number on the outside of the parentheses, and if there's nothing on the outside of parentheses, you can pretend there's a 1, but if you distribute a 1, nothing changes. So we can really just write this as x plus 4 equals -2, and now there's only one step remaining. We need to go through and subtract 4 from each side. X equals -6. So you'll notice compared to the 3 steps up here where I had to distribute, actually you had to multiply twice, then add, then subtract. Here I just had to divide and subtract, and we're done. And you'll start to recognize these problems. You can always ask your teacher if you're like, ooh, is this one of the ones where I can take a shortcut and divide first? And we'll help you out with it. It's nothing too terrible. Let's go ahead, though, and look at 2b and see how things are looking there. On 2b, if we wanted to follow the same process, our first step is to divide by a. That leaves us with x plus b. We don't need the parentheses anymore. How do we write c divided by a? Oh, right, this is the easier literal equation. We just leave it as c divided by a. And last but not least, let's go ahead and subtract b from each side. B is certainly not a like term with the term c divided by a, so we just write them directly next to each other. And we're done. But wait, something kind of weird happens here. You'll notice on 1a and 2a, the answers are exactly the same. But if we look at 1b and 2b, the answers don't look the same. That's kind of weird. Well, they should be the same. Can you guys see how we can maybe manipulate the answer from 2b to equal, from 1b to equal 2b? And it's all about distributive property, right? So if I have this a that's dividing c minus ab, we can distribute the a's division to c and distribute the a's division to ab. Let's see what that looks like. I'm just going to draw a little arrow and we're going to jump into this other guy's box. We're going to get c being divided by a minus, because there's a minus here, the ab dividing by a. Well, that's really, really close to this guy here. I see the c divided by a, but what about this complicated term? Well, what's attached to b? A is multiplying and a is dividing, and we learned in the past that whenever you have a number multiplying and a number dividing, don't they just cancel out? And so I think we are left with c divided by a minus b. So what does that mean? Well, if you and your neighbor get different answers on a problem, then there's a chance you're both right, and one of you just might need to simplify a little bit more to get them to match. Okay, so now I actually have some practice problems for you. If this was a non-COVID year, the directions would hold, where I'd love for you to switch papers with a partner 7 different times or so. So maybe there are 8 problems on here, and I'd love for you to have different handwriting for each problem. You switch, and then you switch back, and you find someone else. And you switch back. But either you're watching this video on your own, or it's a COVID year this year. It's still 2021. So we're not going to switch things. Let's go ahead, though, and see what you can do. So each of these is asking you to solve for a variable. For example, this one says solve for x. This semicolon right here just means that the equation ends and now we get directions. Same thing over here, solve for x. Oh, this one says solve for c. Notice they want you to isolate c here versus x in the equation over here. And so on and so forth. So let's go ahead and see what you guys can do with these. If you ever get stuck, you can always unpause and fast forward me to the problem you get stuck on, but you're going to be able to work through this faster than I'm going to be able to talk you through it because I go more in depth. So try these 8, and then once you're done, you can go ahead and unpause and see how you did and move on to the next page. Ready, set, go. All right, I'm just going to work through each. I'm going to go pretty quickly, though, by my standards, just because there's still more to get through. So 3x plus 91 equals 43. At this point, we should be pretty comfortable that we need to subtract or add to both sides first. I think this gives us negative 48. And of course, you can use a calculator. I don't expect you to be super quick about this, but mental math is never a bad thing. Dividing both sides by 3 gets us negative 16. There were only 2 steps here. We had to subtract and then divide. Let's compare that to part B because they look pretty darn similar. We're trying to isolate x, which means we need to remove the addition and then the multiplication. So I'm removing the addition with subtraction. This gives us 3x equals, less math. See, here you had to do 43 minus 91. That could have been aggressive. But 43 minus c is easy. We just write them next to each other. Moving on, last step, we need to divide both sides by 3. And that leaves us with x equals 43 minus c, all of that divided by 3. Let's look at part C, which is actually still very similar to A and B, but this time they're asking us to solve for the variable or the letter C. If we're solving for C here, let's think about what's attached to C. I only see, no pun intended, 3x adding and nothing multiplying. So I think all I need to do here is actually undo the addition of 3x with subtraction. And that gives us C equals 43 minus 3x. They asked us to solve for C. I think C is solved for. C is isolated. We're done. Even fewer steps. Excellent. Moving on, part D. I'm going to rewrite this quickly. We are being asked to solve for m this time. M is not alone because there's a v on the same side of the equal sign. V is attached by division. The opposite of division, multiplication. Let's multiply both sides by v. These cancel out, and we get m equals, you can keep this as v times d. I'm going to switch the order just to show you that I can. Either one is fine because you can do multiplication in any order. 4 times 3 is the same as 3 times 4. And that's it. Only one step, right? Pretty quick, pretty easy. So don't let these literal equations intimidate you. They usually go quite fast. All right, part E is a party. Y equals mx. Solve for m. I am going to put that invisible multiplication in here so we can see what's attached to m and how. X is attached by multiplication. So let's undo multiplication by division. And that leaves us with y divided by x equals m. Y equals mx plus b. You might have even seen this type of equation before. We're not going to do anything with it though besides isolate b. To isolate b here, mx is adding to b and nothing's multiplying, so I think we should probably just subtract mx from each side. That leaves me with y minus m times x equals b. B is now isolated. 2 to go. D equals RT, another very common equation used in math and the real world. We usually think of this as distance equals rate times time, and we're asked to solve for t. Well, rewriting really quickly, I think there's only one variable attached to t, that's r, and it's multiplying, so let's undo multiplication with division. These two cancel, and it leaves us with d divided by r equals t. 1 to go. This last equation, we're asked to isolate m in y equals mx plus b. I think there are two variables attached to m this time. X is multiplying, and b is adding. We undo the addition first. That gives us y minus b equals m, which still has x attached to it by multiplication. So we're going to go ahead and undo that multiplication, dividing off the x from each side. And that leaves me with m equals y minus b divided by x. You'll notice that I moved the m to the left side and all this to the right, and that's just habit. I like having the variable on the left instead of the right. I didn't do it over here. And it's totally up to you. You could keep it just like this, and that's fine for an answer as well. All right, moving on out. Challenge time. There are 3 literal equations on this page, and each literal equation has, well, at least someone has attempted to solve it for x, but unfortunately they've done so incorrectly each time. Your goal is to first identify the mistake in each of these, and second, then you need to resolve it in the right-hand column. So you need to isolate x in the right-hand column correctly. All right. Why don't you take a look at each of these, and then once you're done, unpause, and we'll see how you did. Welcome back. Let's take a peek. We were asked to solve each equation for x. Well, on this one, let's see what happens. We had x being divided by m equals c, and they decided to undo m. Oh, I see the mistake. This is a really common mistake, too. People said, well, there's a positive m here, and I'm going to undo it by multiplying by a negative m. You can multiply both sides by a negative m, but it's not going to isolate x, because what is a negative divided by a positive? A negative divided by a positive is a negative. So when we divide these two, they don't divide to make positive 1, they divide to make negative 1. So what we've done here is we've left x with still a negative 1 in front of it. If they were both positive, then we'd be done, because we can just have a 1x. But the negative is not quite right. So instead, I actually liked the steps that they tried to do, but let's go through and make sure that we do the correct multiplication. So we need to do x divided by m equals c, and we are going to multiply both sides by positive m. Because a positive divided by a positive stays positive, and positive 1x is just x, and this one is m times c. You could leave it as c times m as well, don't forget that, but they wrote mc over there, so that's where I'm stopping. All right, next one. M divided by x equals c. What did they try and do? They said we're trying to solve for x. It looks like there's division here, and we need to cancel out the m. Oh, so they did something very clever. They said to cancel out the m, we can do 1 over m, and whatever you do to one side, you have to do to the other. Well, let's follow this out. 1 over m times c is c over 1. We multiply fractions straight across. 1 times c is c, m times 1 is m. The right side looks perfect. The left side, the m's do cancel. We can cross-reduce those fractions. But we need to ask ourselves, where is the x right now? The x is in the denominator, and there's a 1 in the numerator. So when we multiply these fractions straight across, x has to stay in the denominator, and there's a 1 still in the numerator. And we have not isolated x. X needs to be in the numerator for the answer. It needs to be in the top of the fraction. This is something that we covered with proportions, so I'm going to go ahead and give you a different way to do this problem. One of my favorite ways to tackle this problem when m is in the denominator is to take c and say, well, we know that we can get rid of fractions by cross multiplication. And cross multiplication works when we have a fraction equal to a fraction. I think we can turn c into a fraction pretty easily. And now, let's cross multiply. X times c, m times 1. So x times c equals m times 1 is just m, right? Anything times 1 is itself. Now we don't have a fraction anymore. So can we see now how we can finish isolating x here? X is just being, or c is just attached to x by multiplication. So let's divide off the c. And that leaves me with x equals m divided by c. How does that compare to the other answer? Oh, they got c divided by m. They flipped the fraction. And we should know that flipped over fractions are not the same, right? What if you had 1/2 versus 2 over 1? 1/2 is like 50 cents. 2 over 1 is $2. $2 is more than 50 cents. So flipping fractions is very important. You do not get the same answer if you flip a fraction most of the time. All right, last but not least, let's see what they did here. A times x plus c, oh, they distributed. Smart, I probably would have done that as well. And they got ax plus ac equals bx, okay? And then they said, well, let's go ahead and get rid of this ax thing. So they divided both sides by ax. Well, what happened here? I see a whole bunch of mistakes, actually. Oof, this person is all over the place. Whoever made this, it was me. Well, b divided by a is attached by two x's here. Those do cancel, so this is right. However, one thing that they forgot is they divided by ax to both sides, but they forgot whenever you multiply or divide, you have to group each side. So if I wanted to do that, I'd have to group this like so. And then the ax would actually distribute to both of these. So it would distribute over here as well. Remember, multiplication or division has to be done to every term on each side. And that's why we always suggest that you follow SADMAP, that you undo addition and subtraction first. Because if you do that, it's going to move everything to one side and you won't have to worry about the multiplication or division part. So they actually made a second mistake as well. The second mistake, they're allowed to do this as long as they remember to divide to every term. The second mistake is a divided by a makes 1, x divided by x makes 1. 1 times 1 makes 1, but there's still a 1 here. And 1 plus something has to be written, right? $10 is different than 1 plus $10. So if you have a 1 that's multiplying, you don't need to write it, but the addition you do. So I think they've actually made several mistakes here. They forgot to distribute their division to everything. They didn't follow SADMAP, and they canceled this out when it wouldn't normally cancel. Well, let's do this correctly then, huh? We are trying to isolate x here. And it's a little tricky because there's bx on this side and there's all this stuff over here. So let us go ahead and take a look. And this one can be a little challenging, but I think you can follow along. So we're going to go ahead and we're still going to take that same first step. I thought it was good. A times x plus a times c equals b times x. Oof. Now, once we're here, I think we're going to have to go through and get all of our x's to one side of the equation. Isn't that what we've done in the past, right? We've tried to go through and get all of our x's to the same side. So I see x's on two different sides here, and we know to move them to the same side we use addition and subtraction. So I'm going to subtract my ax from each side. Oops, that's not a 1. Something minus itself is 0. This gives us a times c equals b times x minus a times x. All right, well, normally if you had x's, you should be able to combine like terms here, huh? Well, that's a little tricky because b and a aren't numbers, so I'm not sure how to combine them. What we're going to do here is something we'll cover more in the second semester, and your teacher probably won't expect this of you on the first semester final. If they do, they'll go more in depth with it later on. What we're going to do is we are going to, and I'm going to use a fancy term, undistribute, which is not actually what it's called. It's called factoring. But we're going to undistribute, and I bet you'll see how it works. So I have a times c, and then notice that each of these numbers have x multiplying times them. Wouldn't that be the same thing as if I had x on the outside of parentheses? What would go in the parentheses that would still make this the same? Couldn't we do b minus a? Right? Isn't x times b the same as bx, and x times a the same as ax? So this idea of undistributing, right, we distributed up here, and I undistributed to get down here, is a very useful tactic that, again, we'll cover more in second semester. But it's always nice to see something early, just so it's not so much of a surprise later on. And it goes well with distributive property. Once we're here, we only have a single x, and this x is being multiplied by this big term b minus a. So let's go ahead and divide by b minus a. And I will divide this side by b minus a as well. This whole term divided by itself makes a 1, and it leaves us with x equals a times c divided by b minus a. And we are done. So again, this last problem I think is pretty darn tricky. I'm just noticing now, too, I think that I numbered this kind of strangely. I think I did A, B, and then D, but oh well, that's a change for next year. Yeah, this last problem is tough, and it's, again, not something that I'm going to expect you to be able to demonstrate, but it's a good challenge or extension for those of you that are getting this super well, the idea of undistributing, or the fancy way to say that is factoring. Okay, let's finish off today's video with a couple word problems, and these go pretty quickly. My computer's having some struggles right now. Easy does it, easy does it. There we go. So we're going to finish off with some word problems. Okay, and I tried to pick 3 problems that maybe you might not run into in the real world, but you can at least see the connections. The first one we're going to look at has to do with temperature, right? We have 2 equations on here. We have the equation F equals 9/5 c plus 32, and then we also have the equation C equals 5/9 f minus 32. And we're told that they are used to convert between temperatures in Fahrenheit and Celsius, right? We need to remember that the United States is very strange in many of the ways it measures things. I think we're stubborn with that. We're one of, I think, only 2 nations left in the world that still use Fahrenheit as our dominant degree of measurement for temperature. Pretty much everyone else uses Celsius. So if you're in another country, you definitely need to be used to either converting between the two, or maybe just going to Google and saying, Google, what's 17 degrees Celsius in Fahrenheit? Is that hot or cold? However, the way that Google does is they use these formulas that I'm presenting right here. So we're going to work a little bit with those. It's good practice to understand where numbers get plugged into formulas, and then we'll try and connect this with what we've done today. So part A. If you were given a temperature of 45 degrees Fahrenheit, and for those of you outside the U.S., 45 degrees Fahrenheit is pretty chilly. It's not quite freezing, but it's pretty close. Freezings are 32 degrees Fahrenheit. And we're asked to convert it into degrees Celsius. Which of the 2 above equations would we use? Would we use the green equation that I'm calling 1, or the blue equation that we're calling 2? Well, you might notice that this 45 degrees, right, we want to turn it into Celsius. This first equation says Fahrenheit equals things happening to C. The second one says Celsius equals things happening to Fahrenheit. we would call this 45 degrees an input. We want to input 45 into an equation, have things happen to it, and then have the answer be a Celsius degrees. So to me, I think we're going to use equation 2. We're going to use Celsius equals 5/9 times Fahrenheit minus 32. And we're doing that because this F right here is the input. It's the known value that we want to plug in. We want to do math to it following PEMDAS, and we'll get an answer that is Celsius. All right, so let's actually do that. Celsius equals 5/9 times Fahrenheit, which is 45 degrees, minus 32. Now, you can do this by hand. It does not actually come out to be a nice integer value, and so I thought it might be a nice time to talk about calculators. In particular, your teacher is probably not going to let you use your phone on the actual exam, and so you probably have to either use a calculator that your teacher has or provide your own that's not on your phone. But we'll talk more about that later on. For now, I want to talk phone calculators because that's probably what most of you have. Every cell phone that I've ever seen has a calculator built in, and some are better than others. I own an iPhone, but I'm going to hate on iPhones for a quick second. The iPhone calculator, I think, is terrible. It only does one step of a process at a time, and I find a lot of students, especially when we get to fractions, really struggle using that iPhone calculator. The newer Android calculators I think are a little bit better, but I wanted to use a cross-platform calculator that everybody can have, and so I'm going to show you how to get there right now. This exists both in every app store, and if you don't have space on your phone, you can also use your internet browser. Now the app itself is super small. It's only a couple megabytes. It's not going to take up a lot of space. But I'll show you how to find it on a browser. So I'm just going to go to DESMOS, Desmos, and then calculator. Now when you search for the Desmos calculator, you're going to see two different options. The graphing calculator is something we'll use in this class later on, but we're not going to use it yet because we're not doing any graphing. We're just going to pull up the scientific calculator. So if you're on the App Store, I would search for Desmos Scientific Calculator, and then check it out. You may have to download it. If you're in your browser, it looks like this. The reason that I like the Desmos Scientific Calculator and the graphing one is I think it handles fractions really, really nicely, right? For example, there are two ways I can do a fraction. I can click the fraction button, which is nice. Or if you didn't want to do the fraction button, I could go through and I could say, well, I want the fraction 5/9, and we need to remember that fractions are just a fancy way to write division. So I can actually do 5 divided by 9, and you'll see it pop up here. Now I haven't done any math with it yet, but you'll notice that it automatically converts it to a decimal, 0.5 repeating. Most calculators will round the last digit because technically it's 5 forever, and your calculator eventually is like, okay, I give up. I'm going to round if I can, and 5 will round up to a 6. But the other really neat thing that I think Desmos does is, last class we looked at the fraction 3/21, and we talked about simplifying it. Here's the decimal version, but simplifying it would mean reducing this fraction. However, if you hit the fraction button over here, right, you can go back and forth between fractions and decimals really easily. You'll notice that it actually simplified my fraction for me. So I think that's a really neat and useful technique. You can play around with the rest of it. It has a keyboard. It has some functions. We won't use really any of these most of the year except maybe absolute value and square roots. But if you go back to the main set here, we're going to go ahead and substitute in 5/9 times 45 minus 32. Try it on your calculator too. Oops, and I'm doing poorly. 5/9. There we go. Nope, I've done poorly again. Second try. 5/9. Excellent. And then you are going to have to go over 1 so that we can do our parentheses, and then 45 minus 32. And then you can close your parentheses and see your answer. 7.22222 if you want it as a fraction, 65/9. But I think we're used to seeing temperatures like this. So we have 7.222. or 2 repeating. It's a good habit to get into to always go 3 numbers past the decimal place. Once you move up in math and you get to maybe calculus or statistics your junior or senior year, they're going to expect you to go at least 3 decimal places. So good practice to do now. And we find it's this many degrees. So for you Celsius folks, 45 degrees Fahrenheit is the same as approximately 7 degrees Celsius. Pretty chilly. All right, let's go ahead and try the other way around. Now we're being given a temperature of 45 degrees Celsius and asked to convert it into degrees Fahrenheit. So which equation would you use? Well, it's certainly going to be the other one, 9/5 times C plus 32. And let's actually do that. Remember, whenever we substitute something in, you should probably group that in parentheses, 45 degrees plus 32. And then this one actually comes out really nicely. You can use the Desmos calculator, but I think you'll find if this is 45 over 1, you can cross-reduce these. You can divide them each by 5. So if I divide my first one by 5, 5 divided by 5 is 1, 45 divided by 5 is 9. So really this just becomes 9 times 9 plus 32. 9 times 9 is 81. 81 plus 32 is 113 degrees. Again, not a bad thing to use a calculator, but don't forget that mental math shouldn't be too terrible either. So, is 45 degrees Celsius hot? Yeah, it's crazy hot. It's 113 degrees. Most of us have never experienced that heat before. Ew. Now, you might have noticed that between these two equations, one of them has a 9/5 and the other has a 5/9. And that is not a coincidence that they have the same fraction but flipped over. Right? Remember, we call a flipped over fraction the reciprocal? So what we're going to try and do to finish off this problem is we're going to solve this equation for C. Because all this is a literal equation. It has more than one variable in it. And we're going to go ahead and manipulate this to isolate C. There are only 2 numbers attached to C. The fraction 9/5 is multiplying, and 32 is adding. Do we undo adding 32 or multiplying by 9/5? Oh, that's right. We undo adding 32 first. So we subtract 32 from each side. This gives us Fahrenheit minus 32 equals, and I'm actually going to leave a space here, 9/5 times C. The reason I'm leaving a space is because although 9/5 is multiplying, and I'm going to erase this, and you could divide by 9/5, it's kind of considered weird to have a fraction inside of another fraction, and it can be a little tricky to deal with too. Instead, we learned on the very first day, lesson 1.1, a different way to undo a fraction. We learned that we can multiply by another type of fraction. We can multiply this fraction by the reciprocal. I'm going to do the same thing on the other side, times 5/9. We can cross-reduce this, and this just leaves us with C. In this one, although you could distribute 5/9, I'm not going to, because you'll notice that this is the exact other formula in our problem. It tells us that Celsius is 5/9 times Fahrenheit minus 32. All right, let's finish off these last 2 problems and go a little quicker today. Identify which operations are currently used in the formula V equals LWH. Now, we've probably seen this formula before. This is the formula for volume of a cube, or maybe volume of we'd probably call it a rectangular prism, right? It's essentially a cube with different length sides. Volume equals the length times the width times the height. Well, the only thing I see in here, and I even said them out loud, is each of these are attached to each other by multiplication. The only operations here are multiplication. So multiplication. All right. Identify which operations you would use to solve the formula for H. Well, if there's only multiplication here, then I think the only operation I would have to use is division. That undoes multiplication. So let's go ahead and solve for H. So what we have here is volume equals length. I use a cursive L so it doesn't look like a 1 times width times height. We're trying to isolate H here. And now notice that because L and W are both multiplying, I can actually do 2 steps in one. I'm going to divide off both the L and the W at the same time. Right? We're dividing by 2 numbers because we're multiplying by 2 numbers. The L's become a 1, these become a 1. They're all multiplying, and we know when we're multiplying by 1s, we don't need to write it. So that tells us then that H is the volume divided by the length times the width. Easy enough. All right, let's try part D here. Lots of typos today, sorry. D says if we know the volume's 24, the length is 2, and the width is 3, find the height. Well, one way you could do that is you could use the original formula and you could substitute in all of these values and then isolate h. But the advantage to working over here is that we can go through and say, well, we already have h isolated, so let's just substitute everything into this formula. V is 24. Remember, when we substitute, we use parentheses. L is 2. Width is 3. Okay? Now, if you do this on a calculator, if you try this on the iPhone calculator and you do 24 divided by 2 times 3, because this is 2 times 3, you will not get the right answer. And that is why I really suggest you use something like this Desmos calculator that does fractions really well. Right? I'm going to go through and we have the fraction on top. We have 24. I'm trying for the 4, but apparently I'm going to have to use keyboard here. 24 divided by, and then this was 2 times 3. And you'll notice that that tells us this is 4. I bet you probably could have done this math too. 2 times 3 is 6. 24 divided by 6 is 4. But if you don't and you want to use a calculator, make sure that you have one where you can do multiple steps at once. All right, last problem. Woohoo! So, speed is measured as the ratio of distance over time. Speed is distance divided by time. And you know that before. You've probably heard speeds on roads in terms of miles, that's a distance, per hour, that's a time, right? Or in most other countries, kilometers is a distance per hour, right? Distance over time. That's how we find speed. So step 1, solve the equation for distance. So S equals d divided by t. Well, to isolate distance, it's only being divided by t, so let's multiply both sides by t. This tells me then, I'll put d on the left side, d is equal to time times speed. Start over, okay? Now solve the equation for time. S equals d divided by t. Now this is where things get a little bit tricky. And the reason it gets a little bit tricky is because this t is in the denominator. And we know when we eventually solve over here, t needs to be in the numerator, t over 1 if you want. So the trick that I showed you before, write these as fractions and let's cross multiply. When we cross multiply each side, and I know there's not a lot of room here, we'll do our best though, we get s times t equals d times 1, that just equals d. And now if we want to solve for time, there's only one variable attached to t, that is the s. So let's go ahead and divide off the s from each side. And that tells us then that time is found by doing distance divided by speed. All right, what's next? How long would it take to travel 270 miles at a speed of 30 miles per hour? Well, let's identify what we have here. 270 miles is a distance. 30 miles per hour, 30 miles per hour, and I'll zoom in here, sorry. Miles per hour is a speed. So we have a distance, we have a speed, we want to know how long. They're looking for a time. So I want to know what the time equals. Do I have any equations that tell me time equals? This is speed, this is distance. Oh, time equals distance divided by speed. Okay, let's go ahead and do that. So time is equal to distance divided by speed, which means time equals distance, that's 270, divided by speed, that's 30. And actually, I can do some mental math here. It's not too bad. The zeros chop off. 27 over 3 is 9. 9 what? Well, what was the what was the time in the problem? Hours, wasn't it? It would take you 9 hours to go 270 miles at 30 miles per hour. 2 problems to go. How far do you drive if you travel 90 miles per hour for 3.5 hours? Well, how far means we are looking for a distance. We have 70 miles per hour. That sounds like a speed to me, 70 miles per hour. And then 3.5 hours, I'm pretty confident it's the time, right? So we are looking for a distance. And so we probably want an equation that has distance. Oh, it's time times speed. So we have our time times the speed, which I did in purple over here. All right, so this tells us then that the distance is going to be found by our time, 3.5, times the speed, which is 70. Okay, so this one you could do 3 times 70, which is 210, and then add 35 on more, or you could of course also do it in your calculator. I'll go the mental math route, and again what I'm thinking is 3 times 70 is 210, half of 70 is 35, and if you add those together that's 245, right? So 245 what? Well, how far? I drove 245 miles. Look at that, if you go 70 miles an hour and go 3.5 hours, 245 miles, you only go a little bit further and do 9 hours if you're only doing 30 miles an hour. Okay, last one. Jason was asked to determine the time it takes for a car to travel nonstop at a constant rate of speed from Reno to Salt Lake City, which is an approximate distance of 520 miles. Jason came up with a time of 150 minutes. Is Jason's answer reasonable? Why or why not? Well, there are a couple things that we're probably going to want to do here. The first thing we're going to do is we're used to seeing speed in terms of miles per hour. So let's go ahead and change minutes into hours. This is something we should probably know how to do too, right? Minutes into hours. Well, let's see. We know that there are 60 minutes in 1 hour, which means if you double this, there are 120 minutes in 2 hours. This is 150 minutes, so we know it's going to be 2 hours. And then I think to get that we add 30 more minutes on, don't we? That would give us 150 minutes. 30 minutes is how many hours? Well, isn't 30 minutes half an hour? So I think 150 minutes is 2.5 hours. So Jason came up with a time of 150 minutes, which is the same thing as 2.5 hours to drive from Reno to Salt Lake City. If anyone has made that drive before, hopefully you're already thinking that, wow, Jason probably exceeded some speed limits, but let's try and prove that. So we have a distance here. So the distance is, of course, the variable d. We have a time, that is t, and let's go ahead and see what his speed would have been then. So speed equals, do we have a formula for speed? Oh, we do at the beginning. It's distance over time. Speed is our distance divided by our time. Okay, let's work this through. So speed equals the total distance, 520 miles, divided by the time, 2.5. And let's go ahead and see if we can figure that out. I'm going to resort to my handy-dandy Desmos over here. So we had, let's clear all of this. We had a fraction, and then I think it was something like 520 divided by 2.5. 208. 520 divided by 2.5 is 208. 208 what? Well, this is the speed, which is found by our distance and time, so it's miles per hour. So Jason's answer is reasonable as long as he drove at 208 miles per hour the whole time. By the way, the speed limit on most roads is somewhere between 70 and 75 if you're going from Reno to Salt Lake City. So that is almost triple the speed limit. I think that is probably not reasonable then, right? Not reasonable unless he is flying in some sort of jet car. So thank you for hanging out with me today while we worked through some literal equations, right? We really just focused on our SADMEP, moving variables from side to side. We did less math than normal. We finished up with a couple word problems. We discussed the Desmos calculator, and that is about it. So next class, lesson 1.6, is going to bring us into the second half of topic 1. We're out of solving equations, and we're going to move into solving inequalities. Thanks for joining me. Keep finding success, and as always, please let me know if I made any mistakes or you need any clarifications or have any questions. Have a great day.